Hi everyone. I just want to take the opportunity to say thank you everyone for joining us this evening. We're really looking forward to welcoming our special guest Martin Woolley from Bluetooth SIG. He is the Senior Developer Relations Manager. For those of you who don't know who I am, my name's Hannah Stevens. I'm the founder of Smart in the City Meetup and Head of Engineering at Oakmont Consulting. So we specialise in IT and engineering recruitment and work with many technology firms across Europe. So if you are looking for a new role or looking to grow your own team, then please do get in touch. So without further ado, I would like to introduce Martin Woolley. And Martin, I think over to you.
Thank you, Hannah. Thank you so much for the introduction. Hopefully you guys can all see me now. So here I am at home, of course, in my incredibly untidy home office, but I'm not ashamed of that. It's the real world once again. So to continue with introductions, I'm Martin Woolley, and I work for an organisation called the Bluetooth Special Interest Group. That's what SIG stands for. My guess is that, given the nature of this group, most of you probably already knew that. A good few of you have probably worked extensively with Bluetooth in your careers. But since I haven't met you and I don't know who you all are, let me introduce the company first. So, contrary to popular belief, that might be exaggerating slightly, but what some people think, we don't make all the Bluetooth. Okay, we don't have a factory that makes the Bluetooth and a warehouse where we store it. We're actually a standards organisation. And the sort of raison d'etre for us really is to bring about interoperability through standardization so that users of Bluetooth devices are free to buy from whatever manufacturer they want, because manufacturers and their suppliers are all implementing Bluetooth stacks to the same sets of engineering specifications. So we're responsible for that, really, working with experts from other companies who are members of the Bluetooth SIG. We evolve and advance the technology over the years. That's what we're basically about. So I just want to say thank you to you guys for coming first of all. Presumably there's nothing good on TV at the moment, so that might change, of course. I make no assumptions. And a big thank you to Hannah for having invited me to speak today, because I do like to come and talk about Bluetooth and do some knowledge sharing. It's quite a key part of our lives as kind of techie professionals, I think. And we live in interesting times, difficult times, I guess, so it's good that we can still get together and do this. So I've got two topics to talk about today. The first is Bluetooth mesh, which you may or may not be aware of. I'm going to assume that everyone is kind of new to the subject, which may or may not be true, and kind of take you through the subject from the beginning. Now, let's start here with the simple fact that Bluetooth is not a single entity these days. There are several flavors of Bluetooth, for want of a better expression. And if you wind the clock back 21 years to the very beginning, a technology we now call Bluetooth BR EDR, that's basic rate, enhanced data rate, that was the original Bluetooth. It's a cable replacement technology. So devices that used to plug into each other with a serial cable got replaced by or updated to use wireless communications, courtesy of this new thing at the time called Bluetooth. And Bluetooth BR EDR is still very much with us today. It's been really successful in a number of areas, not least of which I would say is audio. If you have Bluetooth headphones or headset like the one I'm using right now, actually it's using Bluetooth BR EDR, although that is set to change in the relatively near future. Sitting alongside it, we've got Bluetooth Low Energy. I know you all call it BLE. We don't, because we have brand rules. Bluetooth LE is newer. It's 10 or so years old now, I think, maybe even 12 actually. And the primary design goals behind it, I guess, were originally around creating something which is more power efficient. So power consumption is a critical factor in many types of products, as you all know. And one of the kind of goals here really was to produce something that was very efficient in its use of power. That aside, it's also far more versatile than Bluetooth BR EDR, because yes, it can form point-to-point connections directly between two devices, which is what Bluetooth BR EDR does as a kind of cable replacement technology. But you can also broadcast data. So that means that a single device can broadcast some information, and any number of other devices provided they're in range can receive it. So that's like a one-to-many topology. There is no limits to the number of devices that can receive a broadcast piece of information from a Bluetooth Low Energy device in that way. And Bluetooth Mesh, today's topic, is also based upon Bluetooth Low Energy. So very versatile technology that's been remarkably successful. I mean, the whole thing's quite an amazing story, really. If you've been around for a little while, you'll know that some technologies arrive and go on to thrive for a while, but they get superseded relatively quickly. 20 years is quite unusual for a technology not just to have managed to sort of hang on by its fingernails. Bluetooth seems to be just growing all the time. I haven't seen the stats for this year yet, but the last time I looked, there were over 10 million devices shipping every single day that use Bluetooth, which is a pretty phenomenal number. I think it was 800,000 in the very first year, back in the year 2000. So continual sort of growth as that versatility gets broader and broader, and it gets used in new categories of device. So just to sort of recap the relationship between those technologies. So BR-EDR and Bluetooth Low Energy, think of those as radio communications technologies. Bluetooth Mesh networking actually sits on top of Bluetooth Low Energy in the way that my next slide shall hopefully illustrate. Because we talk about the Bluetooth stack also as if it's a single thing, but it's not. It's kind of fairly modular these days. And even if we focus solely on Bluetooth Low Energy, there are various configurations of stack that are quite valid. Different devices will have different stack configurations depending on what they're for. But generally speaking, the architecture consists of two primary building blocks. The big grey one at the bottom is the Bluetooth LE controller. The one on the top is the host. And sitting in between the two, there's a defined interface called the host controller interface, or HCI, and that defines the way in which those two primary architectural blocks can communicate with each other through commands that go from the host to the controller and events that flow in the opposite direction from controller to event to host. And what you're looking at now is the stack you're likely to find on what I call Bluetooth Low Energy connectable devices. So these are kind of peripheral devices you might connect to from your smartphone. So your smartphone certainly has this stack on it, and almost certainly a Bluetooth BR-EDR stack sitting alongside it. Bluetooth Mesh looks like this. So the Bluetooth LE controller sits at the bottom, and that's providing the fundamental wireless communications capability, courtesy of Bluetooth Low Energy and its underlying hardware radio. But the host contains a whole new set of layers concerned with networking, with mesh networking. I won't bore you by running through what each one of those layers does just now, but I'll certainly kind of drill down into some of them as we progress through the talk. Worth noting at the moment, models at the very top are concerned with largely with messages and message types, and I'll talk more about them most certainly. And bearers at the bottom. Bearer is I guess a fairly standard term used in lots of telecommunications contexts. It defines a way in which the underlying Bluetooth LE controller can be used, and two primary bearers are defined. One provides a connectionless communication capability. So that's using something called Bluetooth advertising, or the broadcast capability I kind of referenced on my very first slide. And the other one uses something that we call the GATT bearer. So GATT is the generic attribute profile over on the left hand side there, and that's connection oriented. So you can do either connection oriented or connectionless communication within a mesh network. But the default and the bearer that must be supported by all mesh devices is the advertising bearer. So most of the time, communication is actually connectionless for various very good technical reasons. So I want to kind of give you a guided tour of Bluetooth Mesh and some of the concepts and terminology. And I'm kind of going to start at the top with some network level concepts. When we perform wireless communication, we are typically accustomed to communication between two devices being constrained by the range of our radio transmitter. So two devices generally have to be in direct range for communication to be possible. If the devices move apart, they go out of range with each other and they can no longer talk. With a mesh network, that's not quite the case. Everything's message oriented. You hear me talk about messages over and over again, and a message transmitted by one device can hop across the network from device to device to device through a process called relaying until it reaches its destination, which may be one or more target devices. Now, a device that's transmitting must be in range of at least one device that's able to perform that relaying function. Beyond that, though, we can do up to 126 additional hops across the network. Now, the range of Bluetooth low energy device to device can be hundreds of meters, depends on the device and the way it's been designed, depends on environmental factors as well. But hopefully you can imagine, therefore, that a Bluetooth mesh network could envelop a very large building with great ease, probably a collection of buildings, a campus, and I do know of one company that were looking at using Bluetooth mesh networking for a neighborhood project as well. Certainly a very large area can be covered with the kind of multi-hop delivery of messages. Multipath is concerned with reliability. So if you look at the kind of fake dotted line pretend graphical network on the screen here, fairly randomly drawn to illustrate the concept, choose any two of the blobs which represent devices or nodes as they're more formally known. You can probably see at a glance that there are various ways that a message transmitted by one of those nodes could reach its destination by hopping via different subsets of the nodes in that network. And if you design your network right, and this is one of the few things that really require careful design consideration, you can design it such that all transmitting nodes have more than one way for their messages to reach their destinations. So that's called multipath message propagation, and the benefit is it gives us redundancy in the network, because if one of those paths is unavailable for some reason, then not to worry, because a copy of your message is being simultaneously relayed across the network via different paths. The first one to arrive will be acted upon. Duplicates are just discarded when they reach the same target a few milliseconds later. Multicast, well, that's a commonly understood term anyway. So multicast is about addressing messages or packets to multiple devices all in one go. And much of the way a Bluetooth mesh network works is designed around multicast messaging. Now, multicast messaging is kind of two things. On the one hand, there are some challenging engineering issues with multicast messaging, depending on how you go about doing it. Luckily, rather than design Bluetooth mesh for relatively straightforward scenarios like residential smart homes with a relatively small number of devices from the very beginning, and I was actually lucky enough to be in the room for the first ever two-day requirements workshop where we were talking about Bluetooth mesh and what it should accomplish and what sort of requirements it should meet. The bar was always set really high from the beginning, and things like commercial buildings were the true target. So some of those engineering issues I'm alluding to around multicast messaging and in fact scalability were addressed right from the start. And one of the benefits of multicast messaging is that it actually helps us with scalability. One of the sort of primary constraining issues around scalability in a mesh network concerns how effectively you make use of the available radio spectrum. So I'm talking about two dimensions of radio here. I'm talking about frequencies and I'm talking about time. So when a device transmits, it's transmitting on a frequency for a period of time. During that period, any other device that's adjacent to it within range that happens to transmit in a time frame that overlaps with the first one will cause what we call a collision. Those two packets using the same radio frequency in the air at the same time will collide, corrupt each other, and effectively be lost. So the probability with which collisions occur is a really key thing to think about when you're designing a networking technology of this sort. Reducing the probability means that you can have far more operations happening simultaneously in your network because the probability of collisions is so much lower. You've got lots of headroom, in other words. So the factors that predominantly govern that are the size of your packets and the speed of your radio. So If you think in terms of logical operations, if the operation I wanted to support was to switch on something, I could define a message type. Now, one technology might require, and I'm going to make up some numbers here, 100 bits to express that operation and provide information that allows it to be delivered to its destination. Another, better, more efficiently designed technology would provide a more highly compressed PDU format that expresses the same semantics in fewer bits, and therefore we have less analog radio symbols that correspond to bits to be transmitted. So it'll be in the air for a shorter period of time, assuming the radios have the same throughput rates. Bluetooth Low Energy, in fact, is the fastest of the low power radios around. It works at 1,000 megabits per second, compared to quite common, you'll see things like 256 kbits per second as the maximum data rate for other technologies. So fast and highly compressed, fast radio, highly compressed short packets, plus multicast messaging, whereby a single one of those short packets is in the air for a tiny amount of time, can bring about a change in the state of hundreds of devices all in one go. So you get an awful lot of return in that tiny transmission when using multicast messaging. So that's what is kind of behind that thinking. It's all about scalability. And again, most of what's going on here is connectionless. There are no connections between these devices. That gets horrendously complicated very quickly. So let's talk about individual devices, or nodes, again, as they're known, and special roles that they can play. So a node in a Bluetooth mesh network is a device of any particular type. I'm going to talk about lighting a lot because that was one of the sort of primary areas that gave rise to the early requirements for Bluetooth mesh. But a light of some sort could be a node, a light switch could be a node, a sensor could be a node, an air conditioning unit, and so on. There are no special kind of networking black boxes in a Bluetooth mesh network. There are no access points, no routers, nothing dedicated solely to performing special networking operations, which you may be accustomed to in other types of network. Instead, what we have are we call them features officially, but they are roles which a device can take on if it's configured to do so and it's able to support it. This is all software. So through a configuration process, you can say, hey, this particular light, I want it to act as a relay. And that's the first of the special roles or features that nodes can play. And I already talked about it because relays are really important. Relays are the devices that make multi-hop and multi-path delivery of messages possible. So as a mesh network designer, one of the things you do is decide which of the devices in your network are going to have the relay function. And relays simply repeat messages that they receive. So if I press a button, a light switch for example, it broadcasts its mesh message. Relays that are in range of it will hear that message and they will repeat it, subject to some parameters in the message. I can control how many hops I want a message to take at maximum. So for example, if I want to switch on all the lights in, let's say, an open plan office space, and I know that it takes 2 hops to reach the far corners of the room, I can make sure that my message has something called a TTL value, time to live, which ensures it goes through no more hops than absolutely necessary, because there is no point my message traveling further across the network than it needs to. But messages get broadcast, they get heard by relays, relays rebroadcast, and they travel across the network in this way. Too many relays, very bad idea, because you'll quickly saturate your network. Just the right number and you'll get a nice mix of simple configuration and design and effective propagation of messages across your network. Now, probably 5% of your nodes are likely to be relays as a kind of rule of thumb that we tend to talk about. 2 other special roles, they kind of work together, which is why I'm covering 2 at once here. Friend and low power node, and I kid you not, yes, they're called friends, and we have a thing called friendship as well in the specifications. So that's nice, isn't it? One way of looking at devices in a Bluetooth mesh network is that they kind of fall into 2 broad categories. There are those devices that will be power rich. They have a ready supply of power. We're not concerned about power consumption, particularly ignoring financial costs for the moment. And we have devices that are at the other end of the spectrum. They're battery powered. The power that they use is absolutely to be kind of safeguarded very, very carefully. And so we can formally designate the latter as low power nodes, and low power nodes have special behaviors that is designed to ensure that they conserve battery or whatever their power source is as best as possible. So here I've got a sensor as an example of a low power node. In this particular case, it may be that this sensor is only supposed to broadcast a message whenever the temperature falls above a certain threshold or below it. So most of the time this thing should be silent. And so far in the story, it's clearly going to be a device that will not consume much power because it only talks, it only transmits message every now and again, a few times a year probably in my somewhat made up example here. Unfortunately, devices have to be available to receive messages as well. There are system messages they must be able to receive, for example. And having the radio on in receive mode will consume power. Now, in a device like this, we have a serious problem because it can be switched on in receive mode because someone might send it a message, but if that's only going to happen a few times a month at most, it's incredibly wasteful. Most of the time when the radio is switched on in receive mode, it will receive nothing. So we're going to burn through a lot of power. So along comes friendship. There's a protocol that's part of the Bluetooth mesh specification that allows a device that's been told it is a low power node through the configuration process to dynamically discover power rich devices who know that they're power rich because they've been told that they can be friends, and reach an agreement, say, hey, can you help me out? I'm a low power node. I really need you to sort of do some of the heavy lifting for me. And so what a friend does is forms this relationship with one or more low power nodes in the immediate vicinity, in direct range of it, and it acts as an intermediary for any messages that are addressed to the low power node. The low power node can go to sleep, be using minimal power, and only wake up, switch on its radio, talk to the friend and say, have you got any messages for me, every now and again, every couple of days or something like this. So I think I have an amazing animation that will show you that working here. So we have a message here that's actually addressed to the sensor. Maybe it's a configuration message. I've decided to change the thresholds for reporting by the sensor. The low power node, the sensor itself, is of course completely asleep at the moment, so the friend stores the message for it and waits until the low power node decides to wake up once a day, once every 2 days, and says, using a special protocol, do you have any messages for me? In which case the friend says, yes, here you go, here's what I received. So it's just a way of allowing work to be kind of distributed across the network in such a way that low power nodes are not disadvantaged. And the last of the sort of special roles is called the proxy node. Now, obviously, there are a great many Bluetooth low energy devices out there in the world. The minority of them are Bluetooth mesh devices, of course. If you think about those 10 million devices shipping every day, some thought therefore went into how we could make it possible for some of those devices to become part of and interact with the Bluetooth mesh network. And that's what proxy nodes do. So a node can support the proxy feature, and proxies basically have two versions of the Bluetooth stack on them. They've got the GATT related stack that I showed you first of all, that allows them to support connection oriented communication, as is the way with any kind of peripheral device. And also they have a mesh stack so they can talk to the mesh network on behalf of the connectable device. And I'm showing a smartphone there, because this is largely for things like smartphones and desktop applications and so on, things that have a graphical user interface, which you're often going to need if you want to manage, monitor and control your mesh network. Smart buildings is one of the primary areas that Bluetooth mesh was designed for, and they usually have people called building managers, and they want to see what's going on in the network. The GATT proxy node makes that possible. Smartphones don't have a Bluetooth mesh stack on them, but they do have the other stack, so you can write mesh proxy applications that can talk to devices in your mesh network. And I'll show you one a bit later on in a short demo. So let's talk a bit more about how devices talk to each other. So I mentioned messages a few times. I did warn you I'd mentioned this many times as we go through this. So nodes communicate with each other by sending messages. We actually talk about publishing, and I'll come on to that in the next slide. And nodes contain what we call state values. So state values and message types are all defined in specifications. State values reflect some aspect of the device in a particular condition that it's in, such as being on or off. And there are then various types of message that that device can send. There are specific types with individual opcodes, and they fall into a number of different categories. So a message can change the value of a particular state on a remote target device. That's done by sending a set message of a given type. A device can request the current value of a particular state value by sending a get message. When a get message is received, the device replies by sending a status message, and in fact, any time a device wants to announce or communicate the current value of one of its states, it sends a status message. So there are three broad categories of message, but there are two flavors of the set message. There are acknowledged messages and there are unacknowledged messages. Now, you are doubtless familiar with all sorts of request response style protocols, so they're all over the place. Every time we access a website, we're using HTTP, which of course is a fairly commonly used request response protocol. It may or may not surprise you to hear that almost all communication in a Bluetooth mesh network is unacknowledged. And the reason for this is that acknowledged communication in multicast communication is problematic. It does not scale well, and it gives rise to all sorts of other difficulties. Imagine my light switch there, if that's meant to switch on 100 lights in an open plan office, and I decide to use acknowledged set messages to achieve that, I have a number of issues. First of all, best case scenario, I'm going to get 100 replies. So very quickly, there's a very big spike in network utilization just because someone pressed one button on the wall. Worst of all, perhaps, my light switch has to manage this, so it has to track the arrival of acknowledgements from all of those target devices. It then has to have some kind of timeout processing. If it hasn't received an acknowledgement in a certain time, it then has to deal with that, perhaps by retransmitting to each device on its list from which it didn't receive an acknowledgement. And if it still doesn't, does it do it again? So you can very quickly generate a bit of a storm of messaging just by pressing a simple button on the wall. And even worse, I think, or is it just as bad? I'm not sure. Of course, the light switch needs to know in advance the identities of all the devices it's controlling. And that means you have to have all sorts of configuration information distributed across your network, and you have to be able to maintain it. It gets very complicated very quickly. So most Bluetooth mesh communication is of the unacknowledged type, and there are other strategies used to ensure that communication and therefore the effectiveness of operations in the network is reliable. For example, usually messages are automatically retransmitted at intervals of several milliseconds, maybe 20 milliseconds, for example, such that if the first copy doesn't arrive, the second one will, or the first one wasn't noticed and responded to. So we work probabilities to make sure that the operation of your network meets reliability requirements, and it works very effectively. So I used one of the words on this slide already, and that was publish. So we use a publish and subscribe communication model. This, of course, is not something we invented. Lots of systems, lots of messaging systems use this kind of paradigm. And the way publish and subscribe works is devices like my light switches at the top of the screen there are configured to publish or transmit messages to a particular address that they're configured to use. That address in this case will be what we call a group address. There are actually three address types in Bluetooth Mesh. We have group addresses, virtual addresses, and unicast addresses. Unicast addresses are unique to each device, kind of. I'm going to correct that definition a bit later on. For now, that one will do. Virtual addresses and group addresses are both ways of addressing collections of devices. However, the membership of each of those collections is not known by the device publishing the message. It simply transmits a message with that group address attached to it in the PDU. On the other half of the screen, I've got some lights. when they're set up and configured, they are subscribed to particular addresses. So when they see a message in the air with an address that they've been subscribed to, they will respond to it. If they see one they haven't been subscribed to, it gets discarded very low in the stack and ignored. So the benefit here is that neither the light switches nor the lights know anything about each other. Consequently, I can change my network with great ease without having to go around and reconfigure all sorts of devices to update their tables so they know about the devices that they control. That's the primary benefit there. It makes life very simple and less costly when we come to managing our network. So I said I'd given you a definition there that wasn't completely 100% accurate, so we'll fix that right now by having a little kind of closer look at the idea of a Bluetooth mesh node. So a node, again, is the formal term for a device that's a member of a mesh network, and they actually have a structure. Some products are more complicated than others, as I'm sure you can imagine. And each addressable part that you want to be able to independently control of a product is called an element. And in actual fact, unicast addresses identify elements within nodes. All nodes have one or more elements, and I'll show you an example later on to make sure that makes sense. Now, elements own things called models, and the way to think about models is this. A model is essentially a specification for or an implementation of a fairly small, very well-defined set of behaviors, of functionality. So, for example, skipping ahead, we have something called the generic on-off server model, and it allows you, that's right, to switch things on or off. Very granular, very precise. And it's inside models that those states that I mentioned earlier on are defined, and all the messages relate to states that live inside models. So there's an example of a product. It's a lighting fixture. In the world of commercial lighting, they call these things luminaires, apparently. And you can see it's got 3 separate LED lights, and my product requirements are that I should have independent control over them, so I can change their, switch them on or off independently, change their brightness and so on. So in terms of modeling this or representing it in code, I will implement my firmware such that this is a single node with 3 elements and a number of models and states implemented within each model, within each element. The kind of diagram on the right there sort of shows you that as a hierarchy. I've got 3 elements there. Each of them has an individual 16-bit unicast address. And to meet my requirements of being able to switch on or off or change brightness, each element has 2 models. There's a generic on-off server I mentioned already, and what we call the lightness server. So lightness is the term used in the world of lighting, which means brightness to you and I, perhaps, certainly me. We do also have a generic level server model, which allows you to turn things up and down. But the reason we don't use that in lighting is that human perception of brightness changes is not linear. I think it's logarithmic, actually, and the lightness server understands that. So you get a more kind of representative set of behaviors that humans expect and are comfortable with that model. And you can see inside those models there are a number of states. Something I probably should have said earlier on, which I'll cover now. Going back to models, we have a separate specification for the catalogue of models that have been defined so far. There are more to come, of course. They break down into 4 families of models, and one of them is called the generics. So the generics list of models contains behaviours that are generally applicable. You can imagine any product type making use of these behaviors, so switching things on or off, changing their levels, things like that. You can imagine all sorts of products, having requirements that those models could meet. There's a collection of lighting relating models, because again, commercial lighting is actually very specialized, and lighting is really important in the world of smart buildings because lights form a kind of natural grid, permanently powered, and they're just waiting there to implement all sorts of special capabilities. The lighting industry even talks about smart lighting as a platform, the idea being that you can deploy code on these smart devices that are also networked and do great things. So lighting is all set to become IT infrastructure, in fact. And we've also got, actually, I'll call it a family of models, but in fact, it's one very generalized model for sensors. Works with any sensor I've ever encountered, that's for sure. And we've got something which we basically contains a small collection of models concerned with time-based activities, scheduling and so on, and automation. So lots of automation scenarios in smart buildings with things like, sensors driving automated adjustments of things like lighting and heating and so on. So that's what we have today. Talk briefly about security. We have limited time, of course, and yes, I've completely lost track of time, but that'll be fine. So I'll briefly tell you about security. First and foremost, a device is only a member of your network if it's been through a process called provisioning. Now, my guess is everyone in this room knows what Bluetooth pairing is. If not at a technical level, you've probably done it at some point. Pairing is a security procedure as it happens. It equips two devices with a collection of security keys that are then used for various security-related operations. Pairing is not useful in the context of a mesh network because it doesn't scale. If you had to pair every possible permutation of pairs of devices in a mesh network, you'd be there for a very long time. And by the way, here's another interesting fact for you. A Bluetooth mesh network can contain up to 32,767 individual nodes. So yes, if you had to pair them all to each other, that would take an awful long time. So there's an analogous process called provisioning. Provisioning is executed typically using a smartphone, and it distributes a number of keys directly to one device at a time. So this is where we use unicast addressing, and we provision each device individually. And it's equipping a device with a particular key that makes it a member of that network. Now, more on keys in a moment, but this is a fabulously drab slide, isn't it? I'm proud of this slide. This took me ages. Some things to know about Bluetooth mesh security. Now, in the world of Bluetooth Low Energy and the connectable devices with GATT and GAP, security is kind of approached as a toolkit, but it is completely optional. So there's a security manager protocol and various security capabilities that devices could have, such as encryption and some privacy related things, but they don't have to have them. It's up to the product designer and the developer implementing that product's firmware to decide what security features to implement. So you have a toolkit, and the idea is that you have to figure out your own security requirements and then implement them. In Bluetooth mesh, security is mandatory because we don't want one device with below par security to weaken the network's security as a whole. That makes sense. Encryption and authentication is applied to all messages, so they're all encrypted using an authenticating algorithm so they can't be tampered with. We actually separate what we call network layer security from application layer security. Applications in the context of a Bluetooth mesh network are whatever you want them to be. You decide this when you're configuring it, but examples would include lighting, air conditioning and heating, for example. We have separate application keys for each of those application areas. The point about separating the security for these two layers of the stack is that something like a light, which is a member of the lighting application, can provide network services like relaying for messages emanating from other applications because it can't decrypt the application layer content of each PDU. It can decrypt the network layer stuff like addresses, so it can provide that network service, but it has no idea what's happening in the higher layers of the stack. You can also achieve something called area isolation, which I find particularly interesting. So each device has a network key that makes it a member of your network, and there is a primary network key, but you can have more than one because you can create things called subnets. Each subnet has its own network key associated with it. Think about hotel rooms. Hotel rooms would be set up as individual subnets. They are each cryptographically isolated from each other. So messages emanating from or addressed to smart devices in one hotel room will not have any effect on devices in adjacent rooms, and nor could you deliberately take control of the teas made or coffee machine in your next door neighbour's room, because area isolation and the way the network keys for subnets work would prevent that from happening. Message obfuscation is applied to all messages. This is designed to make kind of network pattern analysis attacks very hard, stops you being able to figure out patterns of behavior in the network, such as the movement of people with wearable devices, things like that. Common attacks like replay attacks, where you just kind of record and replay a message, can't work. There's protection against that. Trash can attacks are where you dig out a discarded device from the bin, as we would call it, not the trash, assuming you're here in the UK. And you kind of reverse engineer the keys out and use that to launch an attack. There are ways of protecting against and managing that threat as well. And the whole thing starts with the whole secure device provisioning process, which makes a device part of your network, which draws a lot from the world of pairing and uses elliptic curve cryptography to make sure that that process is itself secure. So keys get distributed over a secure link. So keys look like this. I'm not going to spend time on this really, but again, there's a network key, there's a primary one, and you can have subnet keys as well. A number of application keys, entirely up to you how many you have in your network. And application keys are bound to models. That's where the kind of implementation of application behaviors lives. They live in models. But there's also device keys. So every device has a unique key that's unique to it and only it, and that's typically used during configuration. Configuration is one of those occasions where we talk one-to-one with a specific device rather than doing multicast messaging. So it says there that I'm going to do a demonstration now. In fact, it's not going to be live. Far too cowardly to try doing that at an online event with a particularly untidy desk, so I'd have nowhere to put it. But what I am going to do is show you a video of one I prepared earlier in the spirit of Blue Peter, if any of you remember that. Or is it just me? Oh no, I'm so old. So let's start here. Make it full screen. I hope you can see that okay. Let me set the scene by telling you what you're looking at, and then you're going to see some captions pop up, which will pretty much repeat what I'm about to tell you, but at least you should get the information. Mounted there on the right, on top of a high quality piece of cardboard that I cut out from a box, are 16 Bluetooth mesh nodes. Now, these are actually developer boards called Nordic Thingies. You may or may not have heard of the Nordic Thingy. Nordic Semiconductor are, of course, the manufacturer. Dearly love to have been in the room the day they discussed the naming of this product. Yes, let's call it the Thingy. So, was there a massive argument, or did they just all go, yeah, that's a really good idea? I don't know. I'd love to know what happened that day. They contain a Nordic nRF52 Bluetooth module and a large battery. Most of the space there is taken up by a big battery. And the hole that you can see is actually an LED, a coloured LED. So running on those devices is some code that I wrote using something called Zephyr, which you may or may not have heard of. But Zephyr has the Linux Foundation behind it. It's an open source, they would describe it as an open source real-time operating system. It's very kind of device agnostic, platform agnostic. I believe it's supported now by something like 200 target device types or boards. We're not involved in the Bluetooth SIG. We don't kind of endorse it in any particular way, but I like it and use it quite a lot. So that's what I used here. What I've done is included, of course, the Bluetooth mesh stack that Zephyr has. So I have the fundamental mesh networking capability that I need, but I've also implemented 2 of the mesh models so that I have the behaviors that I need for this demonstration. Specifically, I implemented the generic on-off server model, so I can switch the lights on and off, and the light HSL server model. HSL stands for hue, saturation and lightness, and of course that's a kind of color representation scheme. So that's what lets me change the color of my colored LEDs. And I should mention, by the way, that you've probably guessed, but I didn't tell you, so I'm going to do it now. Models come in 2 flavors, clients and servers. Basic difference between the 2 is that servers contain state, so they've got state values inside them. Clients do not, but they produce and consume messages defined as part of that model. So, last thing to know before we look at the demo, each of these devices, through a configuration procedure using my smartphone and an application also from Nordic, coincidentally, I have subscribed each device to 3 different addresses. I have one address that represents the collection of all 16 nodes. I have an address for each column that nodes are in, an address for each row. So each row will respond to messages. Sorry, each device will respond to messages addressed to the entire grid of 16 or to the address associated with the column or the row that it's in. That's kind of the way it's supposed to work. So let's whisk forwards and see what happens. And you get to hear all the same or see all the same things again. So there you go, 6 completely independent devices. And not only did I use cardboard, but I also used glue and Velcro because I'm a proper engineer, me. There you go. It's quality stuff. Each running models. And I wrote an Android application. I've written this application for iOS as well, and I've written a web Bluetooth application as well, just to show you can do this with any of them. So one of the devices is also a proxy. The smartphone app is connected to the proxy. I've selected a destination using my UI, sent an on-off message to the all nodes grid, and you can see that that's caused them all to go on or off. Changing the selected address here, you can see it changing at the top of the screen, sending messages, and only those devices that subscribe to that address are responding. Lots of on-off action going there. We're back to the all nodes address. Switch them all on again, but now I'm sending light HSL set messages, unacknowledged variety, and I'm changing the colors. I'm going to change the destination address again here to select one of the rows, row 3, and now only that row is changing color. So hopefully you kind of get the idea of how this stuff works in practice. Let's stop that, go back to my slides. So I'm going to very briefly show you a little bit of code. Obviously, what code looks like depends on the SDK that you're using and its APIs and the target platform and stuff. This is what Zephyr looks like. So one of the things you'll probably need to do is implement the node composition, which you remember I described in one of my slides. So a node consists of one or more elements. Each element contains one or more models. And largely using macros and arrays, I have described my node composition here. So if you look at it from the bottom, we have a type called BT Mesh Comp. So this is the Bluetooth Mesh node composition. And I've said it consists of an array of elements. My array of elements is above it. And you can see I've got a macro for declaring elements. And I'm saying, well, in fact, that there's only one. And it contains a list of Bluetooth special interest group standard models. You can also have vendor specific models. We do not recommend them, but they're there if you really, really need them. And then the models are declared here again using macros. There are some kind of system models. There's a configuration server, which allows your device to be configured. There's something called the health server model as well, which is to do with fault reporting. And then in this particular code sample, I'm declaring two of the generic server models, the generic on-off, which you've already seen, and the generic level server model, which I did mention. And I'm referencing the definition of the message types by opcode in that declaration as well. So it's pretty straightforward. Creating my mesh node composition is done in a few lines of code, really. Plenty of copy and pasting opportunity there. So here I'm declaring the opcode. So remember, the opcode is a unique identifier for each of the defined mesh message types. And down here at the bottom, I'm mapping message opcodes to functions that will handle different types of message that my node might receive. So hopefully that's straightforward stuff as well. So here's an example of me handling a message that I've just received. So my kind of node composition and association with callback functions for handling particular message types will automatically result in this function being called, and I get a number of structs passed through to me. My message is contained within a network buffer, and Zephyr has some network buffer APIs. So at this point, I've probably got the mesh model specification open in front of me, and I'm having a look at the structure of this particular message type. So I know what fields it contains, and I know what their data type is, and so on. I do things like this. You can see I'm pulling a kind of 8-bit unsigned integer out of the buffer and assigning it to a field called target on-off state. So that's actually the on-off value that is being sent in this particular message type, where 1 means please switch on and 0 means please switch off, and so on. So I work with my network buffer APIs to extract fields, and then I've used one of the various kind of background work APIs that Zephyr has to allow the handling of this state transition to happen off the main thread. And here I'm sending a message. This is also incredibly straightforward. All I'm doing here really is creating a message using, again, the network buffer APIs, but this time to populate the buffer in accordance with the spec for this message type. And then there's a function I make called BT Mesh Model Publish, referencing the model I'm publishing for, and off it goes, the message gets sent. So on the off chance you want to know more, let me point you at some resources. Bluetooth.com is, of course, our website. All sorts of stuff there for all sorts of people, actually. We've got quite a nice collection of resources for developers, some of it's offering opportunities to go hands-on as well. But if we start with reading material, obviously there is the specification or the collection of specifications. You could go straight there. If you want to take an easier path, though, we have a couple of papers I would recommend. One is the one on the left, the Introduction to Bluetooth Mesh Networking for Developers. I think it's 20 pages, but there are lots of pictures. In other words, it's a fairly short, fairly easy read. If you were still traveling to work on the train, you'd read it in a train journey. If you're traveling by bike, I recommend you don't read it and you find some other safer time to do that reading, but it's an easy read. We also have a kind of guided tour really of all the models, because some of the models are simple, some of them are far more sophisticated and complicated. This aims to sort of step back and help you understand how they work, what they can do for you, and what the various dependencies between them are. And then, of course, you look at the spec. If you want to do some real learning, a lot of developers, and I'm one of them, learn best through doing. I can read so much, but I really like to start writing code and seeing what happens. That helps reinforce my understanding, that's for sure. So we have things called study guides, and these are developer education resources, which usually, I think in almost all cases, include hands-on development projects. So you read a bit, you do some coding, you read a bit more, do some coding, and that helps you kind of confirm your understanding as you go through. And they're all at Bluetooth.com in the section marked resources from the home page, so pretty easy to find. So that, my friends, is the first talk done. Now what I'm going to do is switch over to Microsoft Teams. Jerry, well, this is actually a web Bluetooth question, not a Bluetooth mesh, but that's fine. We can talk about anything. So the first question is, how does Apple's lack of support in Safari affect web Bluetooth? So for those of you who don't know, web Bluetooth is a JavaScript API available for some browsers that lets you do those classic Bluetooth Low Energy things like scanning for devices, connecting to a selected device when the user asks you to. You can't do that behind the scenes. And then interacting with it, doing things like reading and writing data values called characteristics. Excuse me. Essentially, web Bluetooth is only supported in Chrome. In Chromium, to be clear. So Google's Chrome uses Chromium. Chromium is an open source browser framework. There are other browsers that use it as well. So, for example, Samsung have their own browser you'll find on some Samsung mobile devices. It also supports web Bluetooth. So Firefox doesn't support it, Safari doesn't support it. I'm actually not sure what the situation is with Microsoft these days, because they abandoned Edge as it was and also shifted over to Chromium. But I'm not assuming anything about whether web Bluetooth is supported there at this stage, because I don't know. How does Apple's lack of support in Safari affect web Bluetooth? Well, you can't use web Bluetooth in Safari. That's the first and probably obvious answer. How does it affect it more broadly? Don't really know. Depends who you talk to. So I guess, I mean, on the one hand, Chrome has by far and away the biggest market share. So web Bluetooth is available to most users, so they can avail themselves of some, excuse me, kind of device-oriented applications, kind of great for sort of remote health monitoring, for example. So web Bluetooth sites could read values from your personal health devices, so things like that. And market share is one of the vectors here, one of the factors rather. One thing that would put me off though as a web developer is that this is not yet a W3 standard, and therefore, it's not completely platform agnostic. How things will progress though, I simply don't know. I'd love to see it as a W3C standard, but that may or may not happen. So Peter says, what are the key use cases where you choose Bluetooth mesh rather than other mesh technologies such as mesh Wi-Fi? I know nothing at all about mesh Wi-Fi, so I can't really comment on that specific. Let me think now. Let's start with availability of products. We could start there. So one of the comparable technologies is Thread. You've probably heard of Thread, I would imagine. I read the last specification, that's all I really know about it. But one of the things that struck me was last year, I was at an event and saw a presentation on this kind of topic actually. And Thread is older than Bluetooth mesh, it's at least a year older. And at that point, early-ish last year, there were apparently only 2 certified, qualified, we call it, Thread devices on the market. So that to me is a bit of an issue, okay, if you can't find the products to use in your network. Bluetooth mesh, there are now, I think, over 600 qualified devices. So the adoption rate has been really tremendous, actually. They're all listed on our website. I'm pretty sure it's over 600 last time I looked. Remember that thing about scalability? The underlying radios of these other technologies are all quite slow. A lot of them use IEEE 802.15.4 for the lower layers of the stack. It can't go faster than 250k bits per second. Don't forget, this is not about raw throughput because we're not transferring large amounts of data in the way that we might do with other scenarios, but we are trying to make the most efficient and effective use of radio spectrum as we possibly can. So brief use of the spectrum to achieve a given network operation is really important. So slow radio is bad. Inefficiently designed protocols with larger packets to achieve the same thing is bad as well. And there are other things in there. I'll tell you what I'll do to give you a better answer rather than spend too long on this. I do know of a really good comparative comparison paper, and it's called A Tale of 5 Protocols. If you Google for that, you will find it, and it actually tells the story of one company's search for the right protocol stack to create mesh networks from. And I will tell you that that company did this work some years ago, went through all sorts of kind of horror stories, discovering the limitations and issues with the other technologies, decided there were no networking no mesh networking technologies that met their requirements at that time, and so got involved with the Bluetooth Special Interest Group and were instrumental in helping create Bluetooth mesh. So they felt there was nothing, but they felt the underlying engineering qualities of Bluetooth Low Energy was the right foundation for building a mesh networking technology that would meet the requirements that they had in the world of commercial buildings, very large scale, very challenging stuff. So have a look at that paper actually, and that'll give you a really good answer there. Dinah had to leave. Bye, Dinah. Sorry to hear that. It's probably something good on TV. You know what would happen. Data rates this is from Stefan. So thank you for the nice presentation. Well, thank you for that comment. What are the approximate data rates you can achieve through mesh? It's not a particularly relevant question. A more relevant question is what are the number of operations that can be handled in the network? Because data rates bring in questions of things like packet size. So in one technology, you'll need those 100 bits to achieve the on-off operation. In a better technology with a more highly compressed packet size, you'll need 30. I think most mesh messages are quite short, something like 30 bytes actually, so maybe bytes would have been better than bits in this scenario. So really you should be looking at how many operations before my network starts to become saturated and not work well, not data rates. So that depends on the verbosity of your devices in your network and its density. So there's a big difference between 32,767 very chatty devices, all very close together in the same room where they're all in range of each other, all using the same slice of radio spectrum, and 32,767 nodes spread out across an entire neighborhood where they're not necessarily sharing spectrum with each other. And these are the sorts of things you should look at. I don't know if I can find it, but let me just see if I can point you at something. Okay, it's on our blog. I won't waste more time doing this. I think the title is something like Putting the Large in Large Scale. So it's a blog post, quite a lengthy blog post about what scalability really entails in mesh networking and what you should really be looking at and how you should understand it. Oh, hello, Mahendra. Thank you so much for attending. So the mesh spec's been out for over 2 years. Where are we on the next release? Well, thank you so much for asking that question, Mahendra, because I suspect you know that I am unfortunately sworn to secrecy on such matters. So the way the Bluetooth Special Interest Group operates is we have contractual relationships with all of our members. So we're actually a membership organisation, something like 35,000 companies are members of the Bluetooth Special Interest Group, and some of them get actively involved in progressing the technology. So they get seconded to our projects, working what we call working groups. And part of that kind of way of working requires that we agree to not leak or release things ahead of time. So level playing field for everyone. So the mesh I've talked about today is Bluetooth Mesh version 1.0, a couple of years old. Obviously, there's more coming, obviously, but I can't tell you details about that just now, but please watch this space. Our website, our Twitter account, and my own Twitter account are great places to look at that. If you didn't see that, you'll see that on the next slide. Thank you, Mahendra. Anonymous. Okay, you mentioned the maximum number of nodes is 32K. Any installation is approaching that size. Do you know what some of the real world mesh sizes have got to? I doubt very much there are any that are right up there. I'm not aware of any mesh networks using any technologies that are that big. I can never remember things like this. I did have a conversation with a company a few weeks ago, and they told me they had a network that was implemented and has thousands of nodes, but I can't remember how many. It was less than 10,000. It might have been less than 5,000, but it's kind of around that kind of ballpark. That's the biggest one I know of. I should pay more attention to the case studies and things that get published, but you know, I'm a bad person. I would imagine if you Google, you'll find some case studies there. I saw a good one the other day. Actually, was Yamaha. I think it's in Japan, and what I liked about this one is it actually had a sort of the return on investment was published where they'd actually managed to reduce their power consumption costs by 25%, quite a large amount of money actually, big 5-figure sum, through creating a smart environment based on Bluetooth mesh, where things like the brightness of lighting was dynamically controlled by sensors, so they're never brighter than they needed to be, and so on, and occupancy sensors, and ensured that things were only on when people were in the room and stuff like this. This is one of the things that drives the move towards smart buildings. Next question from Anonymous. Are the models you talked about both applicable to regular Bluetooth and Bluetooth Low Energy? Is there Bluetooth Low Energy streaming support? Notice how I didn't say BLE there, because my friends in our marketing team would be very cross with me if I said that. So first of all, models only apply to Bluetooth Mesh. And if you remember, Bluetooth Mesh sits on top of the Bluetooth Low Energy controller, just to be pedantic about this, but you know, all techies are pedantic, aren't they? It's one of our lovely qualities. So models only apply to mesh, and therefore no, there are no models for Bluetooth BR-EDR, which I believe is what you mean by the regular Bluetooth. And no, there are no streaming type models for Bluetooth mesh networks, because it's not about that. It's about operations. It's about monitoring and control. That tends to require small amounts of data. And streaming support, well, this is a tricky one. There's no standard profile. So in the world of Bluetooth, we have two types of specification. The Bluetooth core specification is the big one. It's like 3,000 pages, and that defines the stack and how it works. Profiles are smaller specifications that define how you must use Bluetooth for a particular product type or application. So there isn't a standard profile for sort of serial transmission of data over a Bluetooth low energy connection. That's something that Bluetooth BR-EDR is quite commonly used for. There's something called the serial port profile there, which you've probably used. I've used it, but there isn't an equivalent for Bluetooth low energy because it wasn't really designed for that either, to be honest. There are, however, some custom profiles. Again, coincidentally, they're not my favorite. I just happen to know this. I know Nordic Semiconductor have something as well, because I was involved with a device called the BBC Microbit, and it implements their kind of proprietary serial communication profile over Bluetooth Low Energy. They call it the UART profile, I think. Oh, and here's a hard question actually from Glenn. Hard because it's something I don't know too much about. So Glenn says, what is the qualification process for Bluetooth devices? Are these per product, or can we design in a certified device? See the way I bought myself some time there by taking a drink. That's what being a pro is all about. So this isn't really my area. I'm always kind of nervous I'm going to give people the wrong information here. It's all on our website, first of all. The qualification process is fairly clearly defined there. My understanding is that it's both per product and per, sorry, it is per product, but there's a more fast track process when you're using an already certified component. Obviously, the process understands that products are made from components. If you're using and not changing in any way, shape or form an off the shelf, already qualified Bluetooth products, components to be part of your product, then you don't need to go through the full qualification process. You need to do something called listing though. And again, go to the website just to check this. So listing is more of an administrative process rather than a testing process, as long as you're not tweaking or changing that component that you've decided to use. Hope that was good enough for you. Ozak, not a question, just a message to say, oh, very good, thank you very much. That's very nice of you. Oh, bit off topic, but it's a good one. I like this from Stefan. Any news on Bluetooth LE audio? So I sort of mentioned, well, I alluded to this right at the very start here, because I said that Bluetooth BR EDR has been successful in a number of areas, and one of them is with respect to audio. So the headset I'm using right now is a Bluetooth headset, and it's based on Bluetooth BR EDR, something it's been very good at. However, earlier this year, actually at CES, the Consumer Electronics Show, if I can say that, in Vegas, we did make an announcement, and that announcement was that something called LE Audio is coming. So LE Audio is a new Bluetooth audio technology that actually uses the Bluetooth Low Energy stack rather than the Bluetooth BR EDR stack. Now, briefly, because I need to go get on with my next talk soon. Otherwise, you'll all be late for that TV program I keep alluding to, whatever it is. It has a new codec, and the new codec offers higher quality. There are some numbers describing this in more engineering terms. That's the best I can give you right now. But best of all, it supports scenarios or use cases that the old Bluetooth audio does not. So Bluetooth audio using BR EDR, using the various profiles that you may have heard of, is strictly a point-to-point thing. So one smartphone streaming music to your headphones, that's it. You can do that with LE Audio, but thanks to a new set of capabilities, somewhat technical capabilities in Bluetooth 5.2, which is the latest version of the core spec that came out earlier this year, includes something called isochronous channels. Great word. Isochronous channels basically allow you to deal with time-dependent or time-bounded data. So you can deliver the same data to multiple devices and ensure that they act upon that data at exactly the same time. Not hard to imagine audio scenarios where you might want to do that. So if you had two earbuds, for example, they are independent devices, each with its own Bluetooth low energy controller inside. But of course, you want to make sure that encoded audio packets received by those two independent devices are rendered or played back at exactly the same time. That's what isochronous channels lets you do. So it lets you do things like audio sharing. So, if I'm with a bunch of friends and I've got this amazing piece of music that I have composed, I might want to force them to hear that, and I can use that using the broadcast audio capability of Bluetooth LE Audio. You can do some amazing things. I'm going to stop in a moment. You're going to get me talking for too long on this one, so well done on that score. You can do amazing things like have multiple content streams delivered to multiple people simultaneously. So, for example, you could be on a plane. The system on the plane might be about to deliver the safety briefing. You use the panel in front of you to select your preferred language, and in your headset, you hear the briefing in your language. the person next to you hears it in French, the person at the end of the row hears it in Italian, or whatever. So it's really sophisticated, and I think we're going to end up seeing it in things like cinemas. Opera's a good one because it's always in a foreign language, isn't it? Or pretty much, unless you go to the EMEA. And also, it's not just about music, hearing aids. So hearing aids have really stringent power consumption requirements. And to my knowledge, again, not really my area of expertise, but to my knowledge, there isn't a global standard, accepted standard for wireless hearing aids. That's going to change. A lot of the companies that are part of designing Bluetooth LE audio are from the hearing aid industry. So I think it's going to be an enormous thing. However, it's not quite ready. We announced it at CES, but we've still got some work to do in the world of profiles. So the core spec has those isochronous channels. That's the building block. That's the fundamental capability that we need. We haven't finished the profiles yet, so that will come later, but I'm not going to say when, just in case I'm wrong or I get told off. So I hope that helps. Great, thank you for those questions. Hannah, shall we move straight on to the next one and see if I can switch topics?
Yeah, absolutely. If you want to get your next presentation up, then I can send it all live for you.
Well, I think I can do that myself, actually. Let me just try that. There it is. Okay. Just realised I did that whole presentation without my glasses on, which is just, that's like high risk stuff. That's like that's presentation Russian roulette. I think I know what it says. Okay, let me try and, well, I'm sharing my screen already, so let's do that and then that. With a bit of luck, you can now see my next set of slides. Complete change of topic. I need to adjust my brain and get it focused on the right things here. What we're going to talk about now is, per the title, location services and direction finding. So mention Bluetooth to anyone, and I don't think the first thing that they think about is location-based services. In fact, mention location-based services and Bluetooth to someone at random, and I don't think they'd necessarily know what you were talking about. But Bluetooth has been a player, if that's the right term, in the world of location services for a really long time, 10 years more, since Bluetooth Low Energy came along, in fact. What you're looking at on screen is one of the ways that's kind of the world of location services is kind of commonly described or broken down by people like industry analysts. So two big kind of groupings: proximity solutions on the left, positioning systems on the right, and some subcategory of application within that. So we've got item finding solutions. These are usually tags you attach to things, which you then lose, and you can somehow find them, usually from a smartphone application. You press a button, it makes a beeping noise, and you're like, oh, it's over there, and off you go and find your keys or whatever it was. We then have things called point of interest information solutions. Example is proximity marketing, but it's certainly not the only one. This is where you walk into a store and you automatically, by virtue of being close to the, I don't know, the sporting goods department, get told about some tennis equipment that's on sale, or you get some information as you walk through an airport that's kind of location sensitive and possibly is enriched by the fact that the airport system knows what time your flight is, that sort of stuff. So it's all about proximity. Positioning systems are probably quite intuitive. Asset tracking is one example, and the other one is wayfinding or indoor navigation. So GPS, fantastic, but only works outdoors, certainly doesn't work underground. So there is a significant market and opportunity for high quality indoor positioning systems. So that's how the industry analysts see this stuff. In the world of Bluetooth today, number of things already out there. So the proximity profile and the find me profile, I am pretty sure were actually the first profiles I ever wrote any code for. Well, I first got involved in, well, when I got involved with Bluetooth for the second time, I first looked at Bluetooth the year it was released, I think, 20 odd years ago. Yes, I'm old. All right, thank you very much. And then I did other stuff, and then I kind of came back to find myself working on Bluetooth Low Energy in a previous job. I used to work for BlackBerry, by the way. And that's where I became a Bluetooth LE specialist, really. And the The Find Me profile is the one that tags have to help you find things. That's precisely the profile that defines the ability to find a device by pressing a button that sends a message that causes the device to react, usually audibly. The proximity profile is a kind of souped up version of that because it includes that behavior, but also some things that stop you losing the device in the first place. So if you walk away from it, it will let you know if you're going too far away, or in particular if you move out of range so that the connection breaks. On the right hand side, the indoor positioning profile has been around for a while and I don't think has been particularly highly used. That is all set to change. We've got some work to do on this one still actually, but it makes use of the new direction finding capability, which is my primary topic for this talk, and we'll come on to that in a moment. But it's for indoor positioning, it's for wayfinding. The one in the middle is the one where there's been enormous success actually, and this is with respect to things called Bluetooth beacons. So if you're not aware of Bluetooth beacons, this is actually a non-standard application of Bluetooth, and I think I have to credit Apple for being the first to bring the serious kind of Bluetooth beacon to market, and they call it iBeacon. Google followed suit, and they have something called Eddystone. So fundamentally, these two things work the same way. They use the broadcasting or advertising capability of Bluetooth Low Energy to broadcast some data. Both iBeacon and Eddystone can, well, iBeacon will contain a unique ID in its messages, and that unique ID will be associated with a thing or a location. So an application with a database of those IDs can conclude that the fact that it's hearing or receiving a particular ID in a particular broadcast message from a beacon must mean that the user is somewhere near it. They must therefore be in the departure lounge of Gatwick Airport or something like that. Eddystone can do the same thing and more because it has more message types. It can also broadcast things like URLs and telemetry data and stuff like this. But they do fundamentally the same thing, and it's beacons that are used largely in things like proximity marketing and information, kind of context or location sensitive information solutions, but it's also used in asset tracking. I've seen beacons used to create solutions where products are tracked through their different stages in the manufacturing process. So beacons have been really, really successful, and it's ironic that in a way this is a non-standard kind of use of Bluetooth, but it's pretty innovative. And here's something that's obviously quite topical. Now, all over the world, all sorts of different groups, some of them are affiliated with governments, some of them independent, are or have been working on contact detection or tracking type applications. And in all the cases I'm aware of, but obviously I kind of perhaps have a slightly blinkered perspective on the world, they're all looking to use Bluetooth in various ways. Allow a system to be created whereby you get a record of all the people you've been near, all those people you've been close enough to for it potentially to be a concern if it transpires that you are infected with this dreadful virus. So I have seen a number of different approaches, but the main one kind of goes like this. The way it tends to work is this. So the smartphones have an application on them, and each smartphone is every now and again broadcasting a unique ID plus a value which is an indication of the transmission power at a certain reference distance. So usually, so iBeacon has this as well, so does Eddystone. This is essentially a mobile beacon. The TX power reference for iBeacon tells you the power, the expected signal strength at 1 meter from the beacon. Eddystone, it's the expected signal strength right next to kind of 0 meters from the beacon. But you can use that data and the RSSI, the received signal strength indicator at the receiver device, to perform something called a path loss calculation and arrive at an estimate of the distance between the two devices. So that's quite key, because you kind of need to only track those people that have been sufficiently close to you for it to be a worry. Now, it's not very accurate. It's not designed for this. This is just a kind of trick of the trade, if you like, that you can use with any radio-based communications technology. perform a path loss calculation, and in an idealized environment with a few strange objects that kind of distort the signal strength artificially, barriers and humans full of water and stuff like this, it will give you an estimate of the distance from the transmitting device. So that's what these things do. And they take turns transmitting their unique ID and listening for transmissions from other devices, and bit by bit they kind of build up, sorry I've gone too far there, they build up a picture of who was around them over a period of time. So that's kind of the fundamental basis, with some differences that I've seen going on in various places. I just threw that in there because I thought, it's topical and you might be interested in what's going on there. And it's almost the ultimate location-based system. But unfortunately, there is no standard. Nothing in Bluetooth is designed for that application, so people are kind of finding their way sort of on their own there. So back to the main story, positioning without direction data. So here's a scenario where I have a user, let's say with a smartphone application. They're in range of a beacon which is transmitting. The application is receiving that transmission. It knows from the ID in the broadcast message which beacon it's near to, and therefore has some idea of the user's location. It can do that path loss calculation I mentioned to get an estimate of distance, but that estimate is somewhat inaccurate. So there's a kind of upper or lower limit. There's a degree of uncertainty. In other words, so the grey band represents the places that my user might be. I know we're somewhere near that transmitting beacon, the blue blob in the middle there, but I have no idea which side of it I'm standing on, the user is standing on, or exactly how far away. I just have a rough estimate, which may be good enough for my purposes or may not be, depends on the application type. This is how the picture changes though. If I am able to calculate the angle that transmitted signal is coming from, if I do that, then my kind of zone of uncertainty narrows very considerably. I've still got an estimate of distance that is somewhat rough, but because I know where the signal's coming from, I know where I am relative to that beacon. So I can position myself somewhere in that kind of cone shape there. And Bluetooth 5.1, the specification for Bluetooth 5.1 rather, that was last year's release. So early last year, that release came out, and probably its most important change was a feature that allows you to do just this. If you think about item finding, well, I mean, I always tell this story and wonder whether I should do, because it's deeply personal and could be deeply embarrassing, who knows. I'll do it anyway. When I was a kid, family, not friends so much, but family, I think, used to play this game occasionally when I was little, okay, not when I was 18, when I was little, where I had to find a hidden object, and they'd be greatly amused by me walking in the wrong direction, in which case they'd say I was getting colder. If I happened upon walking in the right direction, they'd say I was getting warmer, and bit by bit I'd figure out where the thing was, and oh, fantastic, Martin found the device, isn't he? The thing rather, isn't he clever? Item finding today is a bit like that. No direction data. You kind of might be guided by your application using signal strength in the right direction, but it's a bit hit and miss. Is the signal strength getting stronger or weaker? We don't know. So it can be kind of entertaining to watch people, especially if the thing isn't beeping loudly enough. Obviously, throw direction data in there and the whole user experience gets much, much better. So direction information is pretty useful. And in fact, it can enable new use cases as well. So this is one we dreamed up that we really like the look of. Instead of walking into an art gallery or somewhere like that and getting some information about all of the exhibits in the room, because you're in that room because there's a beacon broadcasting an ID that is kind of correlated with that particular room in the art gallery, I could point my phone at an individual painting. Each of those paintings has a small tag inside it in the frame or something, which is transmitting a special direction finding signal. And through that, I can determine which painting I'm pointing my phone at. And we can filter things by device capability as well. Maybe I want to do some printing and I kind of wave my phone over in a certain direction and it will discover the printers that are over there for me. So lots of cool things can be done with this capability. So let me talk about this new capability, the Bluetooth 5.1 direction finding feature. So there are two methods that are defined that allow you to determine the angle that a signal is being transmitted from. The first one is called angle of arrival, or AOA. And in this one, the architecture looks like this. You have a transmitting device that's transmitting the signal. It's actually transmitting a special direction finding signal, which I'll talk more about later on. Receiving devices have an antenna array inside them. And the angle at which the signal is incident upon each of those antenna is put through an algorithm, and out the other side we get an angle, which can then be used at the application layer for whatever it is that's needed. So that's AOA. Angle of departure, very similar in some ways, but roles are reversed in terms of where the antenna array is. So in angle of departure, it's the transmitting device that has the antenna array, and receivers are single antenna devices. So imagine those beacons in Gatwick Airport. Did I mention that? Yeah, Gatwick Airport has 2,000 beacons in it. Those are what I now call Generation 1 beacons, iBeacon or Eddystone, whichever format they chose. If they were upgraded to be Bluetooth 5.1 AOD beacons, those beacons would act as a transmitter. They'd have the antenna array, and the receiver would be people's smartphones. And this is an immensely scalable technology. Other direction finding technologies that I know of, and I'm thinking of one in particular at the moment, are not particularly scalable for very large numbers of people, because they do things like rely on time of kind of round trip timings of messages, which means that the beacon type device is actively engaged in sending and receiving messages itself, and that will become a bottleneck very quickly. So for scenarios where you've got a large number of people, that other technology, I don't even want to name it, doesn't scale very well, whereas this is completely scalable. Any number of devices can be receiving the direction finding packets transmitted by the AOD transmitter. There's some words on the slides there that I'm purposely ignoring. I'm going to elaborate on them a bit later on. So antenna arrays, I know almost nothing about this subject, to be honest. Everything I know is on this slide. There can be different designs. This is kind of, RF engineer topic. As you can see, they can be kind of multi-dimensional and in different configurations. This matters because at a software level, you need some information about the antenna array design so you can perform the right calculations and arrive at accurate direction values. So I think the word high accuracy was on my my title slide, so let's talk about accuracy. You should be able to achieve very high accuracy location determination, not just angle, to within, let's say, 10 centimeters. And this is possible because with a single direction finding beacon, you can measure more than one angle, and you can see them depicted here on the diagram. You can normally I do this with movements of my arm to indicate vertical and horizontal planes, but you can't see me right now, so I'll use the power of words hopefully to describe this. You can imagine, I'm sure, that we could have an angle on the horizontal plane in a room, and also an angle on a vertical plane. They're called the elevation and the azimuth. That's the sort of term that's used there. If I do calculate those two angles, which I can with the right sort of antenna array design, then I get two lines, and where they cross with a bit of maths, that's my location. And again, in the right kind of conditions, you'll get very high accuracy results, and 10 centimeters is the number I hear talked about from companies that are actually using this. Conditions that are not ideal, lots of barriers, lots of walls and stuff like this, the accuracy will probably be less, and there's probably a good amount of processing of data to smooth it and turn it into a good quality stream to calculate your angles from, but it can be done. Now at this point, I'm actually going to switch to a demo that I wanted you to see because I really like it. I'm hoping you can see what's about to be on my screen. So what I'm going to show you now There's a company, Finnish company I know, who I've kind of met with once earlier this year. Almost the last time I travelled to an event. You may have heard of Embedded World in over in Nuremberg in Germany, huge event. So I went there and I knew this company were going to be there. They're real pioneers of high accuracy direction finding using Bluetooth, and their involvement in that world precedes the standardization that's happened in the Bluetooth 5.1 specification. So they've been doing this for ages. They were then involved in the working group, the project to standardize this, and they have real products out there on the market right now. And I've seen essentially this demo done manually right before my eyes, and it was spectacular. So have a look at this. This is television and sport coming together. So what you're seeing at the bottom of the screen there is a live depiction of the position of the players and the hockey puck. They're into their ice hockey over in Finland. You can see the black thing moving around there, that's the puck. It's stunning. When you see this done live before your eyes, it is spectacular. Now, full disclosure, because the company, they're called Cooper, by the way, you can see the name on the screen there, we're into this before the standard came along. They shared their knowledge and experience in creating the standard. That's the nature of working groups and those projects. Their products may not be completely 100% the same as the standard as it emerged from that process, but it's fundamentally the same, and what it should show you is just how amazing that can be. So sport is one of the sort of areas where this technology is going to be used. So I hope you could see that on your screens. I believe you should have them. So moving on, there you go. One of the things I kind of like doing is understanding how things work, and one imagines that in your line of work you probably are somewhat similar. So what I'd like to do is try my very best to give you a sense of how this stuff works, because obviously there is no magic, there is only engineering and technology. So let's step through the sort of fundamental stuff that's going on underneath that gives rise to these numeric measurements of angle, such that you can create amazing applications like that. So I would normally ask how many of you are RF specialists. I can't do that because I can't see you, but typically I find that a very small percentage of kind of embedded software engineering audience raise their hands. So we all grow up, I guess, using wireless communication, especially in things like IoT devices, but we aren't necessarily specialists. So take a look through at that world through their eyes and just revisit some of the basics. Bluetooth and other wireless technologies use radio. So that's an electromagnetic radiation type, as is light and some other things. And they all have some things in common. Physicists, of course, would talk about waves and perhaps even photons, but we're going to talk about waves as a representation of our signals. And all waves have an amplitude, a wavelength and a frequency. Start here with wavelength. You can see there's like a repeating pattern, an up part and a down part, and then it repeats. The distance between those 2 points on my sine wave is the wavelength. It's not a strange abstract idea, it's a physical thing that you can measure. In Bluetooth, it's around 12.5 centimeters, but not exactly, because it varies depending on the frequency. Bluetooth uses a series of different frequencies from within the ISM, that's the industrial, scientific and medical 2.4 gigahertz band. We kind of divide that into 40 radio channels. This is Bluetooth Low Energy, each of which is 2 megahertz wide. And when devices are connected anyway, we do something called adaptive frequency hopping. So every N hundreds, actually it depends on some parameters, and every so many milliseconds, I'll say for the moment, the selected channel changes. So we're hopping all over the radio spectrum, sitting within the ISM band. This makes Bluetooth incredibly robust and reliable in busy radio environments. And even when we're doing connectionless communication, we're using multiple channels called the advertising channels, which has similar benefits. So wavelength is proportional to frequency, therefore the wavelength will vary, but it's around 12.5 centimeters, and that's good enough for our purposes for the moment. Now, if you imagine a wave traveling over an antenna, at any point in time, if we were to freeze the action, the antenna will intersect the wave at a certain point, and we can describe that point within the wave cycle numerically, and it's called the phase. And phase is measured as an angle, or expressed as an angle, using whatever units you prefer. I'm using pi radians here. You can see halfway through the wave cycle, that's pi. That is pi radians, whereas a quarter of the wave is pi over 2 radians. We could equally use 90 degrees, 180, 270, 360 degrees for the full phase values for the full wave cycle. And that's almost all we need to start to derive angles, because it kind of works like this. Now, you're going to have to look really carefully at the screen here as I try and explain this scenario. What I've got here is a transmitter right in the middle of the screen, and it's transmitting a signal. Now, that signal will emanate outwards from the transmitter in an idealist environment in 3 dimensions as a kind of expanding sphere. Now, I can't think in 3 dimensions like that, far too hard to explain. So let's pretend it's 2 dimensions. It's kind of like throwing a stone into a pond. Energy is released. Ripples emanate from the point of entry of the stone into the pond, and those ripples get lower, get smaller and smaller, the amplitude, as the energy dissipates across the ever-expanding circumference of those ripples. Radio communication kind of works the same way. So, transmitter in the middle, and 2 receivers positioned at exactly the same distance from the transmitter, and therefore on the circumference of that ever-expanding ripple of electromagnetic radiation. Now, because they're at the same distance, because they are receiving the same signal, if I freeze time and measure the phase of the radio signal as it travels over my antenna, I should test you at this point, but I can't hear you, so I can't. I will get the same phase value. It's the same signal, therefore the same wavelength and frequency. Therefore, the point in the wave cycle that's intersecting both antennas at the same time is the same point. I get the same phase value. Great. How does this help me though? Watch what happens very carefully if I move the red receiver, pointed to you right now by the great big and very unsubtle red arrow. I've carefully moved the second receiver device nearer to the transmitter, but I've done so by delta, which is not an exact multiple of the wavelength. If I've moved it by a distance which is a multiple of the wavelength, if I freeze time and measure the phase of both of my devices, I'll get the same number again, because we'll be intersecting the wave that's part of my signal at exactly the same point in the wave cycle. But I haven't done that quite deliberately. Consequently, I'm going to get different phase values from my 2 different antennae. And this helps us with our quest to find the angle that the signal is coming from. Because if we turn this on its side, just to make sure that you're getting this, what we have is this. We have the first antenna, which is a distance of x from the transmitter, and well, a distance of some multiple of the wavelength plus x from the transmitter, and I'm getting a phase value at this point in time of pi, whereas the other antenna is a multiple of the wavelength plus y from the antenna. So you can see I get a different phase value in that case, at the same point in time. So how does that actually help us? Oh, there's some maths on the screen here. How very scary. It works like this. That's my antenna array that I'm describing there in that example. And if, as I will, I know the distance between the antennas in my antenna array, and I know this because I'm the manufacturer, it's my product, then I end up with 3 sides of a triangle. And I can use basic trigonometry. If you guys did mathematics at any point in your lives, you'll doubtless remember sines and cosines and tangents and all that kind of stuff. I'm playing around with triangles in school and hypotenuse and all those sorts of things. This is the basic mathematics required to calculate an angle from that information, the distance between antennas and the phase values delivered to me by measuring it at intervals, a process that's called sampling. With a bigger antenna array, it gets more complicated. And even with the sort of theta angle shown there, I'm going to do some other mathematics that's not specified to make sure I'm getting high quality data. So measuring the phase at intervals in time, that's a process called IQ sampling. A lot of embedded engineers have heard of IQ sampling because it gets used in lots of different applications. It's certainly used in things like audio. IQ sampling measures phase and amplitude of the waves constituting a signal of some sort. IQ sampling is used in receiver devices to measure the phase of what we call direction finding signals that are transmitted by the other end. And I'll talk more about what a direction finding signal is in a moment. And that's the basis from which these angles are calculated. Now, when I first started looking at this, when it was a new thing that was being planned to be released, eventually released last year, you know, my initial reaction was, crikey, this is quite hard to visualize. So I thought I'd write something with which to visualize it. I'm going to show you something now, what I wrote. So it's just a web page and a bit of JavaScript. And what you're seeing, and doubtless amazed by, is the white bar is an antenna. There's a signal traveling over it, massively slowed down. That would normally traveling at the speed of light, of course. The red blob is showing the phase of that signal changing as it's incident upon the antenna. And the number above it that's changing, that's the phase value measured in degrees, moving quite dynamically as the signal travels from right to left. Now, if I add some other antenna to my kind of visualization here, they've been carefully placed. They're not at an exact multiple of the wavelength from the central antenna there. Consequently, you can see before your eyes that the phase value across those three different antenna is different at any point in time. If I switch on sampling, you can see that I'm going to sample from each antenna in turn. Look at the numbers appearing underneath the sample headings at the top there. The most recently acquired sample is in yellow. And I'm just using a simple kind of round robin algorithm there. Other algorithms are possible, but that's the basic principle. IQ sampling applied to each antenna. This is in the angle of arrival scenario. Works fundamentally the same way in angle of departure, except that you have a single antenna that you're sampling from, and you need to know which antenna at the remote device transmitted the signal. So that's that. Let's switch back to the slides and move on. So if you've been following this, and I hope you have, there's a kind of one last kind of fly in the ointment here. Clearly what we need is to know the wavelength such that we can determine distance information as a factor of the phase. So if we know the phase is 180 degrees, we know we're halfway through the wave. If we know the wavelength is 12.5, then that segment of our triangle must be 6.25 centimeters long. Check my maths, but I think I'm right there. So we have to know the wavelength, then we can take our phase values and determine a kind of segment length from that. But there is a bit of an issue here, because the way Bluetooth and many other technologies work, radio is, of course, an analog quantity, but what we want to transmit is digital data. So that's achieved through something called a modulation scheme. And the modulation scheme used by Bluetooth is called frequency shift keying. And basically what we do is we select a channel out of our 40 channels to use. That gives us a range of radio frequencies that sit within that channel. There's a kind of central one we call the carrier frequency. And then to transmit something that represents a 1, we shift the frequency up by something called the frequency deviation. It's typically 185 hertz. So we're still within the selected channel because that has a 2 megahertz width, but we shift it up from that central carrier signal frequency. If we want to transmit something representing a 0, we shift it down by 185 hertz. So we're moving the frequency up and down by small amounts to represent the 1s and the 0s. Of course, this process gets reversed at the receiver to take these analog signals and turn them back into 1s and 0s. But we need the frequency to not change because we need the wavelength to stay the same within our channel. So we can do our IQ sampling and figure out some lengths we can use in some trigonometry. So we use something special, and this is what those direction finding signals really are that I mentioned earlier on. Direction finding signals, and this is defined in the 5.1 and 5.2 spec, have added to the end of them something called the constant tone extension. It's a series of ones, and therefore during the kind of receipt, the receiver's processing of the constant tone extension part of any packet, the frequency will not change. It stays at the frequency associated with the digital value 1, and therefore we have a constant source of material at a fixed frequency from which we can derive a fixed wavelength from which we can apply the phase angle and figure out the length of that segment. That's the kind of final piece of the jigsaw here. That's what direction finding signals are. Now, where does this all sit within the stack? Well, a lot of the action takes place within the controller in the link layer. It only applies to this stack configuration. In the last talk, we looked at Bluetooth Mesh, which has its own kind of set of layers in the host part. So that's what Mesh looks like there. Mesh doesn't have this direction finding capability in it. You can use this in both connection oriented and connectionless communication scenarios. So in both of those scenarios, we can create direction finding packets that have the constant tone extension added to the end of them. All the action really takes place in the controller. That's where the IQ sampling takes place and the production of direction finding packets. But the host controller interface exposes some new commands and events that the host can use to control the whole process. And there are some variables you're going to want to kind of play with according to your application or product requirements. So here's a kind of sequence diagram. I'm not going to spend too long on because we're almost out of time here, but this shows you a connection oriented scenario, and you can see things like we've got two devices, A and B. On each of them, we've got a host part and a link layer in the controller. Host A is talking to the link layer on the same device, and it's setting some parameters to do with receiving CTE from direction finding packets. And then at some point, it's enabling the handling of the production and handling of CTE messages. And in connection oriented scenarios, we then exchange packets between link layers. The first is a CTE request packet, and then the remote device, its link layer, will respond with a CTE response packet. Now, you can see one being sent initially and it gets rejected because host device B hasn't actually got ready. So host B is also going to use some commands to configure its own controller, set some parameters to do with the transmission of CTE packets, and enable the responding to requests it then receives from host A. Hope that makes sense. So there's a bit of a setup phase that the two devices go through, and then they start exchanging packets that contain the constant tone extension, and the receiver device, A in this case, will do some calculations, some IQ sampling. IQ sampling delivers effectively a matrix, multi-dimensional array, if you like, of values relating to the various antenna, throws them up to the host for processing, where frankly the host has a lot of work to do. Most of this then just goes straight up to the application layer, and the application has to do the trigonometry, mathematics, and anything else it wants to do that is proprietary and may allow that company to differentiate from others. There's lots of scope here for differentiating through having better mathematical algorithms to derive better quality results from this same kind of raw material that the Bluetooth stack generates for you. So just like the last talk, let me tell you where else you can go if there's stuff you might be interested in. Of the main stuff, it's all in the core spec, and 5.2 is the latest. This emerged in 5.1, but 5.2 is the latest spec, so that's the one you should be working with. It's pretty well written, all the AOA, AOD stuff in the core spec, actually. I find it pretty straightforward to understand. If you are short of time, though, we have some papers. Direction finding, a technical overview, that's my summary, really kind of takes you through much of what we talked about today. It's a fairly easy read, it's not going to take up lots of your time. We have a more marketing level one as well, that's the one in the middle, and that will tell you more about kind of use cases and market requirements and stuff. And we have some content we have lots of content on our website actually from member companies. So Silicon Labs are, you know, kind of leading company involved in lots of our working groups, very into direction finding, and they've got their own material that we host, which you can go take a look at should the desire take you. And that brings us to the end of the talk. So I'm going to switch back to Teams and find my way to the question area again and have yet another drink.
Yeah, I think there's a couple of questions that have already come through, so I just adding them over now. You should be able to see them on the published side.
Oh, cool. Got it. Yeah, thank you. So what have we got? Let me just absorb this one. Yeah, no problem, Mohammed. So Mohammed is apologising for a long question. That's fine. Because questions about security when using Bluetooth location services. I'm just reading, and I'm very slow, even with my glasses. Okay, right. So to summarise, Mohammed is pointing out that there are security issues with some location-based service scenarios. So I think he's referring to, he's referring explicitly to tags used to find objects that are probably precious to you. So how do you stop other people from seeing or being able to find your devices, I guess, is the answer, the question here. Two things spring to mind. First of all is that these are connection-oriented scenarios, so you're going to be paired with the device in question, which means communication will be encrypted. Other people will not be able to instruct the device to make a noise so they can find it. Aha, I found your wallet. They won't be able to do that because, you know, pairing is the bedrock of all Bluetooth low energy security when it comes to connectable devices like that. So I'm pretty sure those profiles indicate there's always a security section in profile specifications. I'm pretty sure the proximity profile and the find me profile, which are the two possibilities here, indicate that the devices should be paired. So that stops other people from instructing the device from reacting and helping you find it. Visibility of advertising packets is a different thing. They will be visible. Now, all the Bluetooth specs give you to safeguard privacy in that scenario is something called private resolvable addresses. So all Bluetooth low energy packets have an address associated with them. It's a MAC address. You'll be familiar with them from other technologies. Now, one type of address that you can have a device use in its communication, whether that's broadcasting in a connectionless way or when exchanging packets with a connected device, are these special private resolvable addresses. They change seemingly at random. So a kind of casual, malicious or otherwise observer will see what looks like a series of different devices appearing in the environment. They'll just see these addresses. If they're running a sniffer, for example, they'll see this. They'll see a bunch of packets, and every now and again they'll see packets with a different address, and they'll assume it's a different device that they're seeing, and they won't be able to do anything with it because they can't connect to it because it has to use pairing to use this address type. Devices that have been paired with, by definition, because this is what pairing is about, will have a trusted and secure relationship with the other device. And they possess a special security key called the IRK. This is the identity resolution key. And what it does is it allows trusted devices to essentially decrypt, transform the published address back into the true identity of the remote device, so they go, I know who you are. So those are the two things that I would be looking to use in that scenario. And I'm pretty sure the profiles for proximity and for sort of find me related tags do stipulate that you should be using pairing. So hopefully that gives you a reasonable answer to that question. Bye Mahendra's gone. So Peter W saying the 10 centimeter accuracy figure. In actual fact, sorry, I'll read the whole question here. He says you suggested 10 centimeter accuracy indoors. Is there any comparable figure outdoors? Let me just kind of clarify. If I did say that, that's not what I meant. The 10 centimeter accuracy is something you can look to achieve in ideal conditions. So that's not necessarily about indoors versus outdoors. The issue with accuracy and environment largely relates to something called multipath propagation. So radio is electromagnetic radiation, and just like light, it can reflect, it can bounce off surfaces. Consequently, a signal arriving at an antenna, you might get multiple copies of it, one that arrived directly, one that arrived bouncing off the wall, one that bounced off the ceiling. So this is noise, and this is an issue and makes calculations harder. And this is where mathematical algorithms and techniques, things like smoothing, become very important. So nice open spaces like a hockey rink, you're going to get great results there. Outdoors, probably an even better result, depending on the nature of outdoors is kind of quite varied. You're in I did some testing of range, actually. This is nothing to do with direction. I did some testing of range years ago in a local park, which was full of trees, full of people, and actually with my cheapest smartphone, which was one of my kids. So obviously you buy them cheap stuff because they're going to lose it and break it. And a BBC microbit, I still got just under 300 meters range. That was in a very suboptimal radio environment. Change of tack back to the world of direction. Open spaces, whether they're indoors or outdoors, with fewer objects from which signals can reflect or otherwise be changed, attenuated and stuff like this, that's where you'll get the best results. But the other factor is solution design. So there are environmental issues, but there's a whole other level of design expertise required here. It's not just about protocols, it's not just about individual products or devices. There's a solution architect's kind of perspective on this, where in the context of sporting events and buildings and stuff like this, you will be thinking about the nature of the environment that you want this location-based service to operate in. You'll be looking at the height of ceilings. You'll do a kind of survey, and using your experience of the technology in this field, you will decide where your direction finding beacons are going to be, how many of them that you need, kind of density, height above the ground, all those sorts of things. And you may well do some optimization through testing on site. So that's the other variable. So environment brings with it some challenges. You can address some of those challenges through doing a good job designing and testing your deployment. Hope that makes sense. Oh, another one, also from Peter W. Let me just read this. Oh, it's so you're kind of expanding on the last question. So yeah, assume an ideal node on top of a 5-meter lamppost in the middle of a flat car park. Sounds good to me. I mean, you're quite right that things like humidity and precipitation may have some impact. I mean, I think the thing to take away from this part of the conversation is that the Bluetooth stack is going to generate raw material for you. There's still a lot of responsibility at the application layer for taking that data and producing good quality results from it, which is why in some respects it's a fairly specialized area. It's why companies like the Finnish one I kind of case studied earlier on with their hockey thing, they're really good at it because they've been doing it for a long time, and they've become very, very adept at getting good results out of potentially unclean data. My hope, it's not happened yet, but my hope is that if this becomes more mainstream, it's not particularly mainstream yet, what we'll see is platforms providing APIs, and therefore the heavy lifting and the complex maths that may or may not be required behind the scene is taken care of on behalf of the application developer. And you don't need to have quite the same level of expertise, but right now that's where things are. You kind of do really need to have some experience of working with the raw numbers to get the best possible results. It would appear, turning my scroll wheel on my mouse here, that there are no further questions at this point in time.
No, I think they were the last. That was the last one that came through.
Well, my last comment then is once again to say thanks to everyone. Really appreciate you showing up today, and some great questions. I hope that was interesting to you. Thank you.
Yeah, and obviously I just want to say a huge thank you to Martin. 2 fantastic presentations, and I can already see from through those kind of questions you guys asked that the feedback was great. I hope everyone enjoyed it, and in the future Smart and City events, if anyone has any suggestions or wants to do talk, please do let me know. But yeah, thanks again so much again, Martin. And
you're very welcome.
Yeah, if anyone, oh, I think we've just had two. Oh no, everyone's saying thanks, Martin. Thanks, Martin.
Oh, I see it. Thank you. Yeah, thanks, guys.
Yeah. No, thank you again so much, Martin. And yeah, have a lovely evening, everyone. Thank you so much.
Right back at you. Thank you, guys. Bye-bye.
Take care. Bye.